Hey guys, welcome back to the Dynamics video series. This video is going to be covering path problems with free body diagrams. So let's go ahead and get started. So this problem says that the blue 2 kilogram ball is moving in a horizontal circle. The value of L, which is this distance, is 2 meters, and the angle is a constant 15 degrees. Now the rope is going to sweep out to make a cone shape, and we have to determine the speed, or this VO speed, right? So over here I already placed our equations that we're going to need, right? So we have to examine if this is path or if this is polar. This is a path video, so it's pretty obvious that it's going to be path. But in an actual exam, you won't know that. So how do we know? We don't have any theta dot terms. We don't have any r terms like r dot, anything like that. So this is obviously going to be a path problem. So we're looking for speed in our case. So an equation that we're going to use very often is going to be this acceleration equation, just because there's a lot of terms in it. It's got our radius of curvature, it's got our speed in it, it's got v dot in case it's asking for that, and we can determine the magnitude of acceleration. So let's go ahead and write this one down preemptively just to get started. So we know our a equals our v dot term in the tangential direction plus v squared over rho in the normal direction. Okay. And at this point, you got to realize that you have to draw a free body diagram for this problem. Basically, because it's asking for a speed and you're only really given a mass, a length, and an angle, it's going to be a pretty big indicator that you're going to be missing some information, and a free body diagram is going to be necessary. So let's go ahead and draw a free body diagram over here at this point. So let's get our axes correct. So our tangential direction is just going to be in the direction of the motion. So it's told that it's going in line with this arrow. So we can just draw a tangential axis coming out here. And that's going to be our n tangential. And then our normal direction is always 90 degrees, and it's always going to be pointing from the tangential, and it's always going to be pointing inwards towards the center point of this circle. So that's our normal direction. All right, and let's see what forces we have acting on this ball. So it's in the horizontal plane, right? So gravity is going to be acting on it. So I can draw a gravity or force at a distance, contactless force, which is just mg, or just the weight force. And then we also have the tension that is in this cable, yeah, and that is a tension force. And then there's an angle here, and that angle, if you can see it, it's just going to be the same as this theta angle up here. Right? So this is also just going to be theta. And this is 15 degrees as given. So 15 degrees. Okay. Let's see what we can do now. So at this point, we can start summing forces. So we were looking for this top part, right? We're looking for our speed. So let's just sum forces in the normal direction to start, right? If you can see, there's no forces even in this tangential direction, so we won't really have to worry about that too much, but let's just start in the normal direction. So sum of forces, and then in our normal is going to be what? We only have that tension force, so we have T, and then that is the, what is that? That's the cosine of 15. And then no other forces, so that's equal to our mass times our acceleration in the normal, which is equal to our mass times this top component, right? So that's a v squared over rho. Right. Okay, let's see how many variables we have here. So we have our v squared, which is unknown, or just our v. Our mass is known, our t is unknown, and we kind of assume our rho wasn't explicitly given to us. So it looks like we have 3 variables. We can quickly solve for rho, actually, since we know that this L distance is equal to 2, as given. Then the distance here, the distance down here, or this radius of curvature that we want to figure out, is just going to be 2 times the cosine of 15. Not the cosine, that's for the top part, times the sine of 15. And that's equal to 0.517, which is equal to rho, right? Because it's just the radius of this circle, so radius of curvature. So we know rho now. We just still don't know v, and we still don't know our t for this sum of forces. So that's to know we're going to need to sum forces in one other direction, right? So we can get two equations. You might be tempted to sum them in the tangential direction, but if you tried, you just get that 0 equals our mass times acceleration because we have no forces there. So you can kind of know that the acceleration in the tangential is also going to be 0. But what we can actually do is, since this is in a 3D plane, we can sum forces in this, we'll call it the vertical or the y direction, right? So up and down here. So let's just label moving up here as a, it's getting a little cramped, but as a positive y, right? And then down is a negative y. So when we do that and we sum forces in the y direction, we get that a negative mg plus t, and that is a cosine of 15. Oh wait, cosine. Oh, up here I made a little mistake. They can't both be cosine. This one is going to be sine. Good job if you caught that earlier. If you use the angle there, the one that's right next to the angle will be the cosine, so that's the vertical one. And the one in the tangential direction is going to be the sine. So there you go. Fixed. And this is going to be equal to, and then this said that it's tracing out a horizontal circle, and it's not really changing. So this is going to be a 0 because our y value, if you imagine just tracing around the circle with this ball, isn't going to be increasing or decreasing. So let's solve for t here. Since all of these are just numbers, we know that t is going to be equal to our mg divided by a cosine of 15, which is equal to, let me pull this up, about 20.59 or 29. Okay. And now we can plug this t back into this top equation. So let's go ahead and do that down here. So 20.29 times the sine of 15 equals to our mass, which we said was 2 times v squared over our rho, which was 0.517, right? And at this point, we just have one equation, one variable, so we can use our algebra skills or put it in a solver to solve here. I solved it beforehand, and the value of v is just going to be equal to 1.165 meters per second. And that's going to be our answer for this problem. All right, let's start the second problem. This problem's a little different. I think this was an old exam problem. It actually doesn't give you a picture, so you might have to draw it or imagine it yourself. Problem reads, there's a 100-kilogram roller coaster, enters a circular vertical loop of a 10 radius. To prevent the car from coming off the track and the added safety factor, the normal force between it and the track must at least be 100 newtons. And we want to find what is the smallest safe speed the car can have at any point in this loop. So let's just start by drawing this thing. So I'm gonna do my best to draw like a loop. That looks kind of dumb, like a loop. Why is it? Okay, that's not bad. So like a loop-de-loop and a, what's it called, in a roller coaster. And then we were told a couple things, that this thing is circular and that the radius is 10 meters. And that we're gonna have a, at the topmost point, I think it said, what was it? Yeah. When it's on the loop, it must have at least 10 or 100 newtons, right? So let's examine just the top point here. All right. And then we're going to need to do a free body diagram of the roller coaster at this top point, right? So we know a couple things about it. We know that it's got gravity acting on it, right? So it's going to be an mg force. Mg. And we also have a normal force, right? Now, it said this normal force was given at a max of 100 newtons, or no, sorry, at least 100 newtons. So we're going to give it just that exact amount so we can find the smallest safe speed. So let's see. You might be tempted to do the normal force upwards like this because that's what we're used to doing. But if you see this roller cart is on the bottom side of this track, right, the whole time. So if it's pressing into the track, the normal force is actually going to be pressing into it downwards, right? Or in this case, at the very top. If not, it'll always be like pressing this way or pressing this way into this roller cart. So since we're examining at this top point, we can just say that this is 100 newtons going down. All right. And then let's get our axis going, right? So we know this is a path problem. We're going to be using these path equations. So let's get our normal and our tangential direction. So remember, tangential is always in the direction of movement. So that's this way, right? That would be your tangential direction. And then our normal is always towards the center of the circle. And this is the normal direction. Right? So these are 90 degrees. So let's use our normal component, right? So we know that our equation for this acceleration vector is equal to v dot times n tangential plus a v squared over rho for our n normal, right? And then if you want to take a look at this, we're looking for just both of these forces are in the n normal. And we're looking for a v, which is also an n normal component. So we're not going to really need to worry too much about this. Also, there's no forces in that component. So we're really just going to sum forces in the normal direction. So let's do it. So if we sum forces in the n normal direction, we're going to get that. We can treat this way as positive, right? So don't confuse yourself. You always have to treat the positive direction as the direction that the n normal is going. We have a positive mg plus the 100 newtons. And that's going to be equal to our mass times our acceleration in the normal, or just our mass times v squared over rho. All right. And let's see what variables we have. So that's known, that's known, that's known, that's known. The only thing unknown is v, right? So we can actually solve this equation already. So let's plug in our values. So our mass was 100 kilograms times gravity, which is always 9.8. And then plus 100 newtons. And that's going to be equal to our mass again, which was 100 times v squared over rho, which we figured out or was given as 10. Okay, so now we can just multiply, add, and divide and all that, and we'll get a value for v. I did it beforehand, and the value for v turned out to be about 10.39. And this is in meters per second, right? So we know that this is going to be the smallest safe speed we're going to need to generate these 100 newtons, or to keep these 100 newtons anywhere on the track. We know that because we took the extreme case. We're looking at the very top, right? And that's just going to be the answer to this problem. Feel free to reach out if you have any questions about this, and good luck.